Littering is a quiet, fleeting action. A pedestrian drops a bottle without breaking their stride, and by the time a human security guard reviews the area, the person responsible is long gone. Relying purely on a computer vision model to solve this introduces a severe limitation. Drawing a bounding box around a piece of trash is a solved spatial problem, but identifying a piece of plastic does not mean you have detected the act of littering. To an image classifier, a bottle carried in a hand and a bottle abandoned on the pavement are identical static data points. The traditional surveillance approach, continuously recording every camera to capture these brief moments, is expensive to store and raises severe privacy concerns for residents in the area. The engineering mandate for a functional system is strict. It must be event-driven. The software has to analyze frames entirely in the local memory of the device, discarding the footage and only saving evidence when an incident actually occurs. Achieving that requires moving past a basic spatial image classifier. We have to construct a multi-conditional event engine that understands context over time. To build an edge AI system that actually works in the physical world, we have to abandon how we traditionally evaluate machine learning models. The foundation of the system requires a lightweight spatial detector. We use YOLO V8 Small. Its single-stage architecture means it performs one forward pass to identify every bounding box in a frame. That speed is mandatory if we are going to run continuous video on edge hardware. We train this model on Taco, an academic dataset specifically for trash and context. The published dataset contains highly granular categories, separating a cigarette from a plastic wrapper. We merged all of these into a single trash class. An incident report only requires knowing that littering occurred, and merging the labels aggressively increases our examples per class, maximizing training efficiency. We also need images taken outdoors. A neural network trained on perfectly clean, catalog-style product photos of soda cans will fail catastrophically in deployment. It learns to recognize the plain white background rather than the object itself. We use data augmentation as a reality simulator. Shifting HSV values forces the model to interpret sudden lighting changes and heavy shadows. Random erase augmentation simulates occlusion, forcing the network to maintain its lock even when half the object is missing. Robust spatial detection relies less on algorithm complexity and more on violently injecting the chaos of the physical world into the training data. YOLO has a fatal flaw for video: absolute amnesia. It treats every frame as a fresh look, so a bottle carried, dropped, and resting are unrelated. We bridge this gap using ByteTrack to assign a persistent numerical identity across frames. This tracking layer provides the metrics needed to measure behavior. We can now calculate an object's time and position, track its movement trajectory, and confirm whether it is currently stationary. By layering tracking over spatial detection, the AI's output shifts from "here is a bottle" to "here is the exact bottle from 2 seconds ago." With the neural network layers providing identified, tracked objects, we pass the data into a custom human-coded Python logic gateway. This is the engine that actually decides if a rule was broken. Center point perspective distorts geometric mapping, so we anchor logic to the bottom center of the bounding box, where the object meets the ground. This powers 5 conditions: confidence threshold, inside zone, person proximity, stopped moving, and stationary for a confirmation delay. The power of this rule set lies in what it actively rejects. If a person carries a bottle through the zone, it keeps moving. The timer resets every frame, and no alarm triggers. If a bottle is sitting in a trash bin before the camera turns on, the proximity rule fails because no person dropped it there. The algorithm is not searching for trash. It is detecting the precise transition of a state, from carried to dropped to abandoned. While a mean average precision of 0.51 looks like failure, precision is 0.71, meaning when it flags litter, it's correct 71% of the time. However, recall is 0.44, meaning it is entirely blind to over half the actual litter. Why is an engineering team satisfied deploying an architecture that misses 56% of its targets? Video isn't a single photograph. The camera evaluates 13 frames per second, observing objects continuously. We can miss individual frames due to occlusion because the confirmation timer bridges those gaps. If successful hits outlast the delay, the event is confirmed. The inverse is where the real danger lies. A false positive, a failure in precision, sends a fake alert directly to a human operator. A missed frame does not equal a missed event, but a single false alarm wastes operator time and immediately destroys trust in the system. By fusing the spatial detector, tracking memory, and the multi-condition rule set, we generate a cohesive interface. The system captures 60 seconds of footage surrounding the logic trigger and surfaces it for a human reviewer to confirm or dismiss. Because of the aggressive pruning of the dataset and the lightweight YOLO architecture, this entire pipeline runs independently on a standard CPU at 13 frames per second. It requires no cloud compute to function. The system is not without limitations. Relying strictly on spatial proximity to associate a person with a dropped object works well in an empty alley, but it can misattribute the event in a heavily crowded environment. The immediate engineering step to solve this is integrating a pose estimation layer. Instead of just noting proximity, the network will specifically track the kinetic motion of a human arm executing a throw. The core innovation in this project was not the underlying neural network. It was the Python gateway wrapped around it. In the deployment of real-world edge AI, pure algorithmic accuracy means nothing without a meticulously engineered temporal decision layer to interpret it.